Okay, here's just a follow-up video to what we did in class. So in class, again, we talked about starting out with something kids can figure out, which we did a rectangle of some sort, or it could have been a square. And again, when we use arrays early on in life, so again, remember kids have had arrays earlier, so they know multiplication is 4 groups of 3, 3 groups of 4, so they can kind of see that. So that's a natural progression. So 3 times 4 would give you the area of 12 square inches. And so they discover that area equals base times height for rectangles and squares. And then remember we did parallelograms, and I'm just going to make a little bit of dot paper here. And so with a parallelogram, again, we don't have a formula for that shape. So we have to kind of, so I'm going to go over here. And then again, if I like go down to an over one, to draw that, I'd have to go down to an over one to make sure it's parallel. All right. So we use dot paper. And again, we only know rectangles. And so in class, if we were meeting in person, I would have you cut this out. But what you do is, here is your height at a right angle. So you would cut this triangle out and you would physically move it over here. And so then what you get is this rectangle, which again, we know the formula for that. And notice it's still, in this case, this parallelogram is still base, which is 1, 2, 3, don't count dots, 3 times 2, so that would have an area of 6 square units or whatever it is. And so with kids, if they know that they have a square, rectangle, or parallelogram, they know that they can just multiply the base times height and get their answer. And again, I usually have kids do this, so if say, I'm not going to draw the dot paper this time, but say this was 6 inches and maybe this was 3 inches, I would have students write the answer first. So 6 times 3 would be 18 square inches. Because again, when you move this and put it over here, you are literally counting squares. Right? And in class, those plastic squares we use a lot, those are square inches. And so then the kids would write the math that they did. 3 times, oh, sorry, that should be a 6. And then their formula would be based on the math that they did. Now, perimeter, the nice thing about perimeter is in general, perimeter, you just add up the sides. Now, could a kid come up with a more complex formula if they wanted to? Absolutely. So I would let my students do what made sense to them. So say, for example, a square. Like this is, say, 3 centimeters by 3 centimeters. Area, again, is the table that the spaces take up, like when we did the tiles. So some of my students might just do base times height, but I would have some students that would be like, oh, I'm going to just square it. And so their formula might be side squared, where one of their table mates might be, well, it's a rectangle. And so I'm going to take base times height and get 9 square centimeters. So it really doesn't matter as long as their formula matched their math. So I had them work backwards. Start with the answer, show their work, and then create a formula that fit what they did. Now, as far as perimeter goes, same thing. Perimeter is just adding up the sides. So I would have some students that no matter what the problem was, they would just add up the sides. So they're like, that's easy. I can always add up the sides, which is true. So what is that, 12? And again, people are not squares. So again, if you think about string around the outside or people sitting at the table on the edges there, you're not counting squares, you're counting the distance around. And so some of my students would be, all right, that's that formula. Other students would recognize that they didn't need 4 different variables. They still added, but they're like, well, can I just do A plus A plus A plus A because all 4 sides are the same? Absolutely. And then I would have some students that instead of adding 4 times, they would be like, well, I have 4 sets of 3, so can't I just multiply? And that would be what, 4 sets, 4S or 4 per side or 4A, and they would do that. And again, absolutely correct. Now, the nice thing about dot paper is probably when you were in school, in your books, you know, they would give you everything. So this would be like 6 inches, and then they'd give you this as 3 inches. and maybe they would give you the slant is whatever, 3.8 inches. And so, you know, everything was there for you. And so the nice thing about dot paper is students have to work on their concepts of length, height, and other things themselves. So if I have some dot paper here, right, and so maybe this is what, 1, 2, 3, so that's 3, and I'll go over here, 3. So that's what, over 3, down angle, and then we need another, so I need another. This is 3 long, so I need 1, 2, 3, so I need that to be 3 long. Alright, so here's my parallelogram. So the nice thing about dot paper is students have to count, not dots, but distance, 1, 2, 3, so they can get that's 3. They also have to know that the height is straight up and down at a right angle. So that's 1, 2, 3 as well. And then the other thing is to get perimeter, they have to figure out this missing side, which you need Pythagorean theorem to do. So they can pretty much get all their numbers themselves. So for area, that would be, again, I could cut and move that if I wanted to. So if I cut this and move this, you get a 3 by 3 square. So 9 square inches, or whatever we're doing there, base times height. And as far as perimeter goes, I could just be like, okay, fine, I'm going to add up the 4 sides, sorry. But I need Pythagorean theorem to figure out what that one side is. And notice that in your right triangle, this part right here is 2. You see it? 1, 2. So 3 is all of it. So 3 is that entire distance, but this distance 1, 2 is there. And so Pythagorean theorem would be a squared plus b squared equals c squared. 2 squared is what? 4. 3 squared is 9 equals c squared. I get 13. And the square root of 13, I'm going to need a calculator here. So I'll just put that for now. I'm going to add these up just like we do in algebra, but 3 plus 3 is 6. 1 square root of 13 with another one is 2 square root of 13. And so this student might go A plus B plus C plus D, but another student might go A plus B plus B. Some students might double A and double B, and I'm going to go grab my calculator quick so we can put that in decimal form. So that's actually a perfect answer right now because obviously I didn't round the square root of 13. But if I figure out what the square root of 13 is, okay, about 3.6. Okay, then I could go back, right, and do, you know, maybe some students just want to add all 4 sides. So 3.6 and 3, 3.6 and 3, and add up those, which again is what, 6, 12, is that 13.2, I think. 13.2, and again, inches or whatever. And again, it's perimeter, so it's not going to be squared. And then the other thing you have to be a little bit careful of is sometimes students cut and move to find areas. So they cut and they move this over here to find the area, which is great. You can see that 3 by 3. The problem is you can't find the perimeter of that square because area is movable, but perimeter is not. So you have to, even if you cut and move it for area, you have to go back to your original shape. Because this is where people are sitting, that's your perimeter. This area here is the same as the blue square, that's fine, but not perimeter. So you have to go and make sure you do perimeter on the original shape. Alright, so really, that's what we have right now, is that for those shapes, you can do base times height, you can add up all 4 sides, and then tomorrow we'll move on to the next one. And basically, if you know these 3 kind of columns, you can find the perimeter and area of anything. So, all right, I'm going to pause the video and we'll pick up there tomorrow.